Okay, so now I'm going to explain to you a couple of product rules for differentiating vectors, which are very natural. So again, thankfully, you don't need to know a lot of new techniques. It's just the ones that you would have expected all along. So for example, let me just start with the addition rule, which is very intuitive. So it's almost something that you would have guessed even if I had not written it. But say that you had two vector functions of time. Then if you wanted to take the derivative of the sum, you would just take the individual derivatives. So for example, if a of t is just t squared 1, and b of t is minus 1 2t e to the t, then the derivative for the sum, again, it's obviously useful to see it on an example, but if you do the example, it looks a little bit silly because you could just always say, well, why don't you just add them first and then differentiate, right? And that makes a lot of sense. That's probably what you would do, but this is just to illustrate the rule. The next video will actually show you why it's useful to know these rules, and it's not just like silly as this might suggest. So the derivative of the first one is 1 to t 0, and the other one is 0 to e to the t, and that's just the same as 1 to t plus 2 e to the t. Okay? Let's see, which is the same that you would have obtained if you had added them together first and then differentiate, as you can check. A more interesting differentiation rule is a product rule for dot products. So let's think about dot products. In this case, the derivative with respect to time of a of t dot b of t what is that supposed? Well, what would this be if this were like an ordinary multiplication? It would be the derivative of the first one times the second one. That's true still in this case, but now the multiplication is dot product, so you have to put dot product here. And then the first one, derivative of the second one, and again, this is all good, but you just have to remember that to put a dot product here. And so as an example, which again is a bit silly because you could always do the dot product first and then differentiate, but say for these two, the same two vectors from before, what this would be saying, the rule is saying that you take the derivative of the first one, which is, as we explained before, is 1 to t 0, dot the second one, and then plus the first one dot the derivative of the second one, which is 0 to e to the t, and this gives you -1 plus 4t squared plus 2t squared plus e to the t, which is fine. It's like just some quantity. Now already here I can do a less trivial example, I don't want to erase this because I guess it's better to refer to it for the next computation. But so let's do a more interesting situation where you have, say, planet Earth. Well, it looks like the sun, but it could be the sun also. And you have like a satellite orbiting the Earth, okay? And so let's suppose that the satellite, I mean, obviously as the satellite moves around the Earth, right, the position vector is changing. But so R of t is changing, but let's assume that the magnitude of R is not changing, so it has a fixed distance from the origin. Assume so meaning that like it's like moving like in a circle about the planet Earth. So what happens here? Remember, so let's call this constant R for the radius of the circle. So the magnitude of R of t is R, right? If you square both sides, you get R squared. Now remember that the norm squared of a vector is the dot product of that vector with itself. So far I haven't done anything interesting, but now here's the key. Now I can differentiate both sides of this equation. This is more. It's nice to see what happens here. So the right hand side will just give you 0 because that's the derivative of a constant. If you apply the product rule to the left hand side, it's the derivative of the first one dot the second one plus the first one dot the derivative of the second one. But the derivative of position with respect to time is just velocity. So you get v dot r plus r dot v equals 0. But remember, it doesn't matter if you dot product. It doesn't matter the order in which you find things. So this is the same as 2 v dot r equals 0, which means that v dot r equals 0. In other words, velocity is perpendicular to the position vector. So when you move at a constant distance from a point, the velocity vector has to be orthogonal to it. Okay? And so this gives you like a nice application of the product rule. Because it gives you like a very straightforward consequence of like a very naive, very simple assumption, which is that you are moving with a fixed distance from some point. The last differentiation rule is the one for cross product. Which again is similar to the one for dot product. But you just have to replace dot with cross. So the derivative of the first one times the second, but now times becomes cross, plus the first one times derivative of the second one, but now the times becomes cross again. So probably this is what you would have expected. The only thing that you do need to be a bit more careful here is that if this is A and then B, you have to put A and then B, A and then B, because you cannot flip them around. Remember that A cross B is not the same as B cross A, so you have to preserve the order in which they appear, otherwise they would give you the wrong answer. And then, well, since I erased the formulas for A and B, let's do this example, which is a bit faster than the one I had intended before. So the derivative for the cross product of A and B, again, since here is with concrete expressions, you could do the cross product first and then take the derivative of that, but that would not be illustrating the cross product rule. The next video will show you that it is actually useful to have this rule. But for now, let's just assume that this is something interesting to do. So if you follow the recipe, you take the derivative of A, which is 1, 0, 0, cross B, which is 1 e to the t3, and then you would do A, which is t negative 1, 2, cross derivative of B, which is 0 e to the t 0. Okay, and okay, so this is you can use the formula with determinant, but in this case it's fun to do it with the other expression. So this is I cross I plus e to the tj plus 3k plus ti minus j plus 2k cross e to the tj. Again, it's also possible to do it with the determinant formula, but it's not too complicated here. Remember our diagram. It's just to practice doing it differently. So I cross I is 0, I cross j gives you k, so you get e to the tk. I cross k gives you negative j, so you get minus 3j. And then you get I cross j is k, so you get t e to the tk. And then j cross j is 0, and then 2k cross j is negative I, so you get minus 2 e to the t I. Okay, so you can leave, you could leave the answer, I guess, that way, but if you want to group these things together, this is negative 2 e to the t, negative 3 e to the t plus t e to the t. And that would be the formula for the derivative of that cross product. So again, you can do this in different ways. You can do it with the determinant formula, or you can take the cross product first and then differentiate and check that that gives you the same answer.